All right, so let's go ahead and get going. First thing that I'll point out is that we do have a problem set that is due on Friday. We've already done everything for that problem set in terms of the lecture. Even before the Friday lecture we had done. So, and in the Friday lecture we finished chapter 3. So we're going to go ahead and start in with chapter 4. Okay. All right. So the topic of chapter 4 is energy. So just to be clear, what we've done so far is we've done motion, solving for motion with an equation of motion, which is Newton's second law. And now we're talking about conservation laws, and so far we've done momentum and angular momentum, and now we're moving on to energy. All right. So so the things that we're going to do in this chapter are going to involve some math. And again, it's fine with me that if you feel rusty, you can rely on me to always present. So one of the things that we'll be using in this chapter is the del operator. All right. And it is equal to the partial with respect to x times the x direction plus the partial with respect to y times the y direction plus the partial with respect to z times the z direction. Let's remember that in those partial derivatives, we get to treat all other variables as they are constants. All right. And we'll be using this del operator to calculate the gradient, or the grad. So let's say that we take the gradient of a function f. Okay, so in that case it is the del operator acting on f, which is a scalar function of maybe x, y, and z. And that will give us the partial of f with respect to x in the x direction plus the partial of f with respect to y in the y direction, and the partial of f with respect to z in the z direction. All right. Also, we will be using the curl. And when we do want to think about the curl, it has to be the curl of some sort of vector function. It won't apply to a scalar function. So here I've got a vector function f. And so if I want to take the curl of that function, take the cross product of the del operator with the vector function, which gives me the determinant of the following. So I've got x hat for my first row, for x hat, y hat, z hat for my first row, and then the components of the del operator, partial with respect to x, partial with respect to y, partial with respect to z for the next row, and then the components of the vector function, so fx, fy, and fz for the third row. And in order to evaluate that, I know we've already done cross products, but I'll just illustrate this again. That gives me x hat times the 2 by 2 determinant that is left over if I take out its column and row. So that is times dfz dy minus dfy dz. So I'm just taking that 2 by 2. All right. This guy minus that guy. All right. Minus the y hat, which is the next element over from x hat, times the 2 by 2 determinant that's left over if I remove its row and column. So that's dfz dx minus dfx dz plus, again, now I'm going to my next unit vector z hat, times the 2 by 2 that's left over, determinant of the 2 by 2 that's left over, I'm going to take out its row and column, which gives me dfz dx minus dfx dz. All right, so as those come up, I will probably just sort of remind you that we're using them, but
That's not right.
that's wrong. Oh, I'm so glad. Yeah, you're right. That z's not right. dfy dx, thank you, minus dfx dy. Perfect. Well, I assume, unless there's another error. Okay. Yeah, so everything in the x hat term should depend on z and y, which it does. Everything in the y hat term should depend on x and z. Everything in the z hat term should depend on x and y. Thank you for catching that. All right. So these are this is just the math that we will be using at times. So let's go ahead and get started. The first thing we're going to talk about is the relationship between kinetic energy and work. And probably from 240 to 250, you remember that there is this work kinetic energy theorem. And indeed, that'll be the relationship that we wind up with. All right. So first things first, let's go ahead and define kinetic energy. And sometimes I'll just use KE for that. That's sort of what I'm used to, but I'm going to try to transition and be consistent with your author who uses capital T. All right. And clearly for a single particle, that's just equal to 1/2 the mass of the particle times the speed of the particle squared, which would also be the velocity of the particle dotted with itself. Okay. So we are going to think about what if I have a single particle and it is moving through space. So we will say, I'll go ahead and make sort of a coordinate system here, x, y, that here is sort of a path along which it might move. Maybe here's a point that I will call location 1. Oh, I should have labeled that on the other side. Okay. And here's a displacement that I'll say is small enough that I can call it dr. In which case, here is another point that I would call R1 plus dr. Okay. So what we want to think about is how the kinetic energy might change as I go from R1 to R1 plus dr. All right. And I'm going to advance this displacement dr in an amount of time that I'm going to call dt. All right. So if I want to think about how its kinetic energy changes, it might make sense to think about the change in kinetic energy. And specifically, I think about the change in kinetic energy divided by the change in time. Kind of confusing because it's dt, but time rate of change of kinetic energy. All right. So I already have an expression for kinetic energy, so I'm going to make a substitution here. So that's the derivative with respect to time of 1/2 m. And I'm going to remember that v squared is the dot product of two vectors, where each vector is velocity. Because that'll allow me to take my time derivative using the chain rule. All right, so I've got 1/2 m times time rate of change of velocity, which is v dot, dotted with v, plus v dotted with v dot. You guys okay with that? Okay. And so I wind up with 1/2 m times 2 v dot dotted with v. So my 1/2 and my 2 will cancel, and I get m v dot dotted with v. And this m v dot is interesting to me because I know from Newton's second that that's the net force that's being applied to my particle. So the time rate of change of the kinetic energy of my particle is equal to the net force on my particle dotted with the velocity of my particle, which is the time rate of change of the particle's location. So I'm going to just go ahead and substitute dx dt for v. Oh, that should be r. Sorry, I do that often. I apologize. Your author uses r for location. Okay, so the next thing that I want to do here is just multiply both sides by that infinitesimal increment of dt. And I get that the infinitesimal change in kinetic energy is equal to f dot dr. Okay, well that's not bad. That's a pretty good result. And that's an important enough result that I'm going to go ahead and give it a name. This is the differential form of the work kinetic energy theorem. Okay. But now I want to think about what if I went ahead and integrated both sides. Well, in order to do that, I sort of want to think about an initial situation, which would be maybe my particle at R1, that's fine. But I'd want sort of some final situation here. I'll call that R2. I don't want to draw that arrow because it'll mess up the way my figure looks. But so I want it to be not just an infinitesimal change. I want it to be a finite change that's associated with that. Okay. So now what I'm going to have to do is integrate both sides. Once I want this finite change, that means I want it from point 1 to point 2. So what I would like to be able to find an expression for would be like T2 minus T1, right? What is that equal to? And obviously, another way to write that would be the delta T, so change in T. And so in this case, what I could do is I could break my path into these little drs, obviously, and if there were finite drs for which the force and the dr were constants, then I could think of this as sort of a sum. F dot delta r, if such terms were possible. But really what we tend to do is we tend to take the limit where delta r becomes infinitesimally small, in which case this summation becomes an integration. All right, and that's the expression that is equal to the difference in kinetic energy. And you might be saying, why didn't I just integrate both sides from initial to final? Exactly. Completely true. Good point. I'm just trying to follow this logic because, again, I'm trying to just introduce the book to you on my first time through. All right. So that's a fine statement, but we're probably more familiar with the statement T2 is equal to T1 plus the integral. And in this case, I could be very specific because R1. Because I know my variable I'm integrating over is location, and I get f dot dr. I'm going to put a box around that. This looks a whole lot like our other conservation laws. This reminds me of our conservation of momentum expression, which we expressed most generally in the impulse momentum theorem. The same sort of expression that we got for angular momentum And now we see a similar type of expression for energy, and we're going to call it the work kinetic. In fact, it's an expression for kinetic energy. I'm sorry, not energy, kinetic energy. So this is called the work kinetic energy theorem. All right? Okay, and it states that the final kinetic energy will be equal to the initial kinetic energy plus the work done. And by the way, let's remember that everywhere where I have an F, it represents net force. Okay? So the work done by that net force and going from location 1 to location 2. All right? So this is probably a great time to clarify that I'm going to call this thing that shows up in this integral, I have to give it a name because it's very important. So we're going to define that as the work. And in this case, it's the work done by the net force. So I'll call it W sub net. And it's the integral from location 1 to location 2 of F net dot dr. You could also note that if there were multiple forces adding up to this net force, that I could make a substitution here. So F1 plus F2 plus and so on, however many there are. We'll say there are n forces acting, dotted with dr. Okay. And that is equal to the integral. I'm just going to shorten R1 to R2. It just says integral from 1 to 2. F1 dot dr plus the integral from 1 to 2 F2 dot dr plus the integral from 1 to 2, oh, plus and so on until integral of 1 to 2 Fn dot dr. All right, so that all holds. And indeed, for each of these terms, I'm going to notice that this is the work done by force 1 along that path. And the second term is the work done by force 2 along that path, plus and so on, plus the work done by force n along that path. And we see that these works, even though they come from things that are vectors, and in fact, integrals of dot products of vectors, they themselves are just scalars that add like scalars. The works themselves. Okay, so that is nice to know. All right, so the next thing that I want to point out, again, clearly this is our first, in this class, our first line integral. So we should talk a little bit about line integrals. So in this expression, I'll just take maybe one of these terms here. I have work done by the first force is equal to the integral from R1 to R2 of F1 dot dr. Okay. And hopefully I've made it clear that as you do this integral, your dr is going to be the infinitesimal bit of the path that you continue to travel. So, and then as you integrate them, you'll be adding them up like so. All right? So you kind of have to know the path that you're taking in order to calculate work so that you understand what line you're following. All right. So we'll just point out that this object here is called a line integral. It can also be called a path integral. All right. All right, so just reminding ourselves what each of these things are that we're taking the dot product of, R1 to R2, of fx in the x direction, plus f sub y in the y direction, plus f sub z in the z direction, dotted with dx in the x direction, plus dy in the y direction, plus dz in the z direction. All right, and so those dx, dy, dz, they are the components of your dr. Okay, and what I wind up with here is the integral from R1 to R2 of fx dx plus fy dy plus fz dz. Okay, so I think that that's pretty clear, but it probably wouldn't hurt us to do an example. Let's do the example. All right, so in this example, we're going to calculate a line integral. In fact, we're going to calculate specifically the work done by a force and my force is going to have a specific form that's a function of location, so we're just going to choose a random function of location. We're going to have y in the times x hat plus 2x times y hat. Okay. So we're going to calculate the work done by this force for my object, which is going to move from the origin to the point 1, 1. Along each of the 3 paths shown. So let me give you the figure that goes with this problem. So there's the point 1, 1. Okay. The first path is going to go from the origin along the x-axis until it gets to the point 1, 0. And then it's going to go up in the y direction to the point 1, 1. We will call that path A. The second path will be a straight line from the origin to the point 1, 1, and we'll call that path B. And the third path is probably as complicated as a path as I'm going to need you to be able to do, so that's a good thing. And it's going to be a fourth of a circle that extends from the origin to the point 1, 1. So that'll be path C. All right, so I am going to go ahead and start working. I'm going to do A first, so let's all start doing A first. And if you finish A, please move on to B. You guys need that up there still? Okay. If you're stuck, please talk to somebody. So this is from 0 to point P. Okay, Q. Oh yes, you're actually using this. Okay, so for me, I point out that Q was the 0.10, and so all right. So, but this is fine because you figured out that all along this line, your x component, of course, is 0, right? Okay. And the next one, we have, you're at a location out here along this line where the value of x is 1. Yeah, good. Is it coming? Okay, good, yeah. No, this isn't
Yeah.
correct.
That's what I'm looking at.
Okay, that's fine. I'll go ahead and pick that one up in a moment. Wait, what did you get for the first? It's,
Yeah.
very good.
Because then
This first one is, you have,
go
it's along
in, so
this
it'd be
path.
the along the 0, so it should, so if it's along the 0, then it should, then there's no,
Right.
okay. Makes sense. Thank you.
Mhm. So we have to break this one up, because it's sort of a discontinuous path. We have to break it up into two paths. The next ones won't be that way. This is the one where we have to make it two integrals. Good enough. I'm going to go ahead and start working. All right. So for the first one, I have to break it up into two parts, because this is a discontinuous path. So what I'm going to note is that in part one, I have dr, which is equal to dx, so what do I say? Dx in the x hat direction. All right, because I'm going to have a little increment of path like that. All right? And in part two, I'm going to have dr that is going to be a little increment like that. So it'll be dy in the y hat direction. And so what I have to do is I have to integrate my two paths. So I'm going to say from my initial location, which is 0, 0, to this location. Some of you guys used Q, which is fine, but that is 0, 1. I have to integrate f dot dx times x hat, which is just going to give me fx dx. Okay? Yeah? All right. And then for my second piece of the path, I'll go from 0, 1 up here to 1, 1. And I am going to have f dotted with dr, where dr is dy times y hat. So that will just give me fy dy. And I probably should have been clearer here, where along this path, x will always be, will go from 0 to 1, but y will always be equal to 0. And along this path, x will always be equal to 1, but y will go from 0 to 1. Okay. So let's go ahead then and evaluate some stuff here. The x component of force is equal to the y component of location. And in this case, the y component of location yeah, that's wrong. All right, so I went from 0, 0 to 1, 0. And 0, 1, here should be 1, 0. Okay. So I go from 0, 0 to 1, 0 here along this path. All right. So everywhere here, my y value is 0. My x component of force is equal to y. So I have the integral from 0, 0 to 1, 0 of 0 dx. All right, and for my y component of force along this path, I see that it is equal to 2 times x, and for all points along this path, x is equal to 1. So I get the integral from 1, 0 to 1, 1 of 2 times x, which is 2 times 1, times dy. Okay, so obviously my first integral is 0. My second integral is 2 dy, where y goes from 0 to 1. So it's just 2 times y, which I have to evaluate from 0 to 1, or 2 times 1 minus 0, or 2. Okay. So let's go ahead and do, unless there are there questions about part A? Let's do part B. And I am not sure how much of this you guys have seen in your calculus. You guys done line integrals in calculus? Okay, okay, great. Then I'll give you a couple minutes to do part B. let me tell you something about part B because I'm kind of worried. In this case, we just have one path. We don't have to treat it as two paths. And it's a path along a line, y equals x. So say just one path is needed, and it's along the line y equals x, right? And if y is equal to x, that's useful, but also that means that dy is equal to dx for along this line. All right, every time that you do an incremental step, like so, your infinitesimal change in x will be equal to your infinitesimal change in y. All right? Okay, so let's see if we can use that information. Okay. All right, so I'm going to go ahead and start working here. All right, so I've got just one path here, already written out what that means, so I need to just go ahead and calculate my integral. Work done along path B is going to be equal to my integral of fx dx plus fy dy. From the origin to my point P, yeah, I'll go ahead and call that point P, along the path shown. All right, so let's go ahead and substitute in some things. Fx is y, dx, plus fy is 2x, dy. And I can take this down, noting this relationship between the two variables, I can turn this into a one variable integral. So wherever I see a y, I'm going to substitute x. So I'll get x dx plus 2x, and wherever I see a dy, I can make the substitution dx. So now I'm just down to one variable, and because I have one variable, I can very simply just put the values of that variable now of my integral, and I get 3x dx is what I have to integrate over, and I get 3 times the integral of x dx, which is x squared over 2, which I have to evaluate from 0 to 1, and I get 3 times 1 squared over 2 minus 0, also known as 3 halves. You might be wondering, hey, what about our units and stuff? Not all of this is unitless, it's pure numbers. So this is just the value. All right. So are there any questions about that one? Let's go ahead and do part C, and I'm not going to have much time to give you a chance to work on this. But this is, whenever you go along a line, it's important to write the equation for the line, and notice that the equation for the line gives you a relationship between the two variables, and you can turn it into a one variable integral. That's the thing I want you to see here. Okay? And that will be quite common, following along a line. This next one is along a portion of a circle. That could come up at times too. It kind of doesn't show very well, but okay. All right. So now I want to calculate the work along path C. Again, this is just going to be just one path needed. It's not a discontinuous path. And along this path, all points x, y, it will be easier to think about this point here, sort of that dr, if I define, since it's a portion of a circle, if I define this as an angular displacement about the center of the circle. Oh, that's supposed to say theta, by the way. All right. So if I make that definition, then my x component is going to be 1 minus the cosine of theta. Because cosine of theta is this distance here, and what I want is what's left over, so it's 1 minus cosine theta. And my y component is just sine theta. In that case, I'm sort of making a change of variables to a single variable. Again, so I can just have a single variable integral along this path. Because in this case, I notice that my dx, where x is equal to 1 minus cosine theta, is equal to my derivative of the first term, which is a constant, so I get 0, minus the derivative of the second term, which would be minus sine theta d theta. So here I'm going to try to make a change of variables to this theta variable. All right? And dy, similarly, will just be cosine theta d theta. All right? Which is actually kind of useful. It means as I move along here, my dr is always equal to sine theta x hat plus cosine theta y hat. That's kind of interesting when I make this choice. All right. Anyway, so now that I have it down to just one path, let me go ahead and calculate the work. Okay. P of fx dx plus fy dy. Let's make some substitutions here. Origin to P. Fx is going to be y, which is sine theta. So let's remember this guy here is our value for x. This guy here is our value for y along that path. All right, so I've got sine theta. And then I've got dx, which is also sine theta d theta. Let me write that sine squared theta d theta. All right, plus fy, which is 2 times x, where x is 1 minus cosine theta, times dy, where dy is cosine theta d theta. All right, so now I've gotten this path integral down to the form of just a single variable integral. And now I have to think about my limits on theta. Theta is, in order to travel along my path from my origin to P, theta has to go from 0 to pi over 2. And now I've got sine squared theta plus 2 cosine theta minus 2 cosine squared theta d theta. Oops, d theta. You can look them up, but I did want to also model this for you guys. This is fine with me. If we just go to, let's Wolfram alphas. I'll just search. Go to Wolfram alpha and do this thing. You guys are probably way better at this than me because I actually still do look them up. Well, let's do it. So I'm going to Wolfram alpha. I'm going to type in. And I want to take the integral of Well, it's not really helping me as much as I thought it would, but that's okay.
Symbol F's better.
Am I having a problem here? Okay, sure, I'll take this one. But then I need to alter it. Sine squared x plus 2 times cosine x minus 2 times cosine squared, which we do with the caret 2, of x. And I already close my parentheses. And I'll get my indefinite integral here, which is there. And then I'm out of time, doggone it. But you can evaluate that for the case where x is equal to pi over 2 minus the case where x is equal to 0, okay? And you see how it goes? All right, well, that's enough of that. We'll do some more out of this chapter on Wednesday. I'll see you then. Let me shut off my recording before you ask this question.